So, demystifying parallel programming in Python, this is our talk. But first of all, Guten Tag, Darmstadt. To introduce myself quickly, my name is Gaël Pegliasco. I'm French, as you can hear it. I've been developing from Python since more than 20 years. And actually, I'm doing a lot of computer science on parallel programming on supercomputers. I'm most of the time a Python trainer. This is my most important work. And I've got a very fluent French English, as you can hear. So in this talk, we are going to speak about parallel computing. And for this, we are going to take the time to present the hardware basic. This is very important when you do parallel computing. You need to understand how works your hardware, to understand why you get the performance you were expected, or why you don't get those performances, and how you can change that. So we are going to have a look on processor first, then on play with the processors. Then we'll have a look on the landscape of Python parallelization libraries, looking at concurrent programming with code examples. And finally, we'll try to speak about the future, quantum processor, photonic processor, and a few others. So starting with processors. If you want to do perform parallel programming, you first need at least a computer. I've got one here, that's perfect. And inside the computer, at least multiple processors to run one program by processors for the old processors. And with the next generation of processors, a processor with at least multi-cores. A core is a compute unit inside the processor. We are going to explain this in a few seconds. But which kind of processor can we use with Python? CPU, the processor running your operating system, GPU, your graphic card, which is used for machine learning also, TPU for machine learning, or quantum processors, or others, because they are others. So when speaking about processor, we usually focus on CPU, the central processing unit that is running your personal computer operating system. But you also have GPU, the processor running your graphic card, used for machine learning too. But there are other types of processors that also exist, like GPU, Tensor processors. We are going to explain them later. NPU, quantum processor, photonic processors, and a few others. So let's start by the most common, the central processing unit. This is the processor inside your laptop that runs your operating system, your Windows operating system, your Mac, Linux, or other operating system. And there are many manufacturers for that. This is not a question of the point here, so I won't present them. To use your processor efficiently, you need to understand the internal architecture and its behavior. So three concepts are required. Sorry, I haven't started my chronometer, and it's important. Okay, so three concepts are very important to understand when you do parallel programming in your processor. The first one is the frequency, the processor frequency. The second one are the cores inside the processor that can run your different program or function or different part of code, and the hyperthreading technology attached to them, and the processor cache and memory. And in Python, even in Python, which is high-level language, all these processor properties will have impact on your code. Fortunately, to discover this functionality, we have, on Linux, for example, some useful commands to inspect the hardware. Let's start with lscpu and swlock-ls. So I take my terminal, maximize it, and enter the command lscpu. This command will display your processor hardware. Enter. A lot of data are presented. We can see the brand of the processor. This is an Intel i9. We can see the number of sockets. Do you know what is a socket? You can just raise the hand, don't reply. Okay, the socket is a place on the motherboard where you put your processor. So here I've got one socket. It means I've got only one processor in my computer. Okay. The processor owns 14 cores. It means I can run 14 different programs at the same time. And there are threads inside the core. I will present thread a bit later. We can see also the processor frequency. Also, by raising the hand, just raising the hand, do you know what is clearly the frequency of the processor? few people, yes? So the frequency is most of the time explained as the speed of the processor. This is not very accurate, but it's a good idea. In fact, you can think about the frequency as a number of operations your processor can execute per second. So it's expressed in megahertz. So this one can run from 400 megahertz up to 5,000 megahertz, 5 gigahertz. So it can execute 5 billion instructions per second. It's quite a lot. This is not completely accurate. This is not, in fact, instruction. It's about cycle, but we will speak about that a bit later. And then, regarding the processor, we also have internal memory. This is a text description of the processor, not so easy to read, so we can focus on the graphical map of your processor that can be displayed by hwlock minus ls command. Yes. I have to be root to execute it. And I've got a beautiful picture of my processor here. Do you read it? I don't know if the backend is okay. So let me try to explain. We can see here the different cores of the processor. So each core is a compute unit in the processor that can run a different program or a different Python function. Okay? Some cores have what is called hyperthreads. 2 hyperthreads there, no hyperthread there. So hyperthread has the data that we were seeing just before with the thread, 2 threads per core. Processor also get an internal memory that is cache memory. When you work with your processor, so your processor doesn't directly work with the outside RAM that is on the motherboard. It takes the data inside the motherboard, bring it back into its internal cache, and start working on it. This has been created before this century. Processor didn't add cache, didn't have cache. Sorry for my tenses. Processor didn't add cache. They were working with the external frequency on the external memory, sorry. And the external memory was as fast as the processor to update data. But processor has grown in frequency and memory has grown in size despite of the frequency. So now the external memory is too slow for the processor and this slow down your processor. So to prevent from this, your processor owns an internal memory, very slow memory. You see it's a 24 megabyte for the biggest one, and 1 megabyte here. 48 kilobytes is very, very little. But when your data are stored inside this internal cache, your processor can run at its maximum speed. And it is not limited by the external speed of the memory, the external memory on the main board. Okay? Perfect. So we've got internal memory that we can see, we've got cores, and we've got hyperthreads. I'm going to speak about hyperthread quickly, and we will see that in action a bit later. So hyperthreading is a new technology to do input-output more quickly in your computer. Imagine this case. Your computer is, so when you've got an hyperthread here, I've got 2 hyperthreads, so this is a hyperthread, sorry, let me explain. An hyperthread is a logical unit inside a physical core. A physical core can run 1 program at a given time. I've got 14 physical cores, so I can run physically 14 programs at a given time. If I run 100 programs at the same time, only 14 could be executed at a given time. Okay? So in some cores, I've got 2 hyperthreads. This is 2 logical cores, 2 logical units. I can load 2 different programs in each hyperthread. Sorry for my English. In each hyperthread, but only one can be executed at a given time. So let's imagine this one is running, the thread number 10, and sometimes it's doing some I/O, input-output, writing to the hard drive, getting data from the internet, and this is slow, some milliseconds. 1 millisecond, when you run at 1 gigahertz, it's 1 million, yes, 1 million of instructions that you do not do. It's a lot of wasting time, wasting operation. So at this moment, the core said, hey, you are doing nothing, I'm bored, I'm boring, this is boring me. I'm going to switch to the other hyperthread and running this code. This one is suspended while the data are coming. and the second one is running. So when you run a server that is doing a lot of I/O, input-output with the hard drive, working with external peripherals, hyperthreading is very useful. When you do heavy computation, hyperthreading is not useful at all, and at the opposite, it's an issue. It's a side-back effect. It will slow down your computer, and we'll explain that later. But so remember, hyperthreading is a good technology when you do a lot of I/O, because you can switch between two functions of the same core each time one function is doing some I/O, some input-output, writing to the disk, speaking with the internet. So this is very efficient. You don't lose time. But when you do heavy computation, this has some drawbacks, and you prefer to use core without hyperthreading. So when you choose your computer, I will explain that later. But when you choose your computer and your processor, if you want to do heavy computation, take a computer with many cores with no hyperthread. If you do an internet server with a lot of I/O speaking with the network card, use hyperthreading. It's okay? Perfect. Let's continue. So here we are the command. So I've explained what is the processor frequency. It is the number of instructions the processor can do in a second. If this is not entirely accurate, the exact definition is the number of cycles. So the processor frequency refers to the number of clock cycles it can execute per second. That is to say, a clock cycle is the minimum time required to perform a basic operation, such as changing the state of the transistor. This is to be perfectly accurate. So changing the state of a transistor means, for example, switching a bit from 0 to 1. You've got a minimum time to do that. This is the computer cycle. Okay? Perfect. Some instruction in your computer may require only one cycle, for example, inverted a byte, and some may require much more cycle, for example, doing an addition, a multiplication, or a cryptographic command. We have spoken about the frequency. We can play with the frequency in your computer. There is a command in Linux, cpuFreq util, that allows you to switch the frequency. Let's have a look at it. So I've prepared some command. We have seen that my processor have a frequency that can go from 400 megahertz up to 5,000 megahertz. I'm going to put all the cores to 400 megahertz, the lowest frequency. So I'm going to slow down my speech. Now, and now I'm going to run a Python program, IPython. Oh, sorry. I'm doing a very heavy computation, 2 plus 2. A lot of time to measure the minimum time required to do, the average time to do this computation. So to do this computation, my computer takes at this frequency 78 nanoseconds. Okay, I quit IPython, sorry. And then I'm going to change the frequency to the highest value. More than 10 times faster. Will my compute time will be 10 times faster? Let's have a look. Ready? Go. Set and go. And yes, it is more than 10 times faster. Okay? So for you as a developer, you want the maximum speed, but for example, you are in the train, in the ice, and there is no power plug. Oh, and you have to finish your work. You can slow down your frequency and work a bit longer, because at a low frequency, you consume less power. Okay, it's fine for everybody? I continue. So, I skipped some slides that are not so interesting. There is a technical wall about frequency. Actually, the maximum frequency processor can have is 6 gigahertz. If you try to go above, there are some side effects on the computer, and the data are wrong, or the computer warm too much and can burn. The computer, sorry, the processor. The processor warm is too high, and it can burn. So to work, to overcome this limitation of the maximum frequency in our processors, multiprocessor machine first emerged, then followed by multi-core processors. Let's have a look. This is a multi-processor computer. So you've got two processors under the ventilator on the radiator. Here you can have two processors. Each one can run one program at a given time. If there are many cores, many programs at a given time, each one. So they share the same memory and they consume twice energy. If you want the next year have 2 times more power, you add 2 more processors, so 4 processors, then 8, 16, 32. Industrial have gone up to 32 times, 32 processors on the same motherboard. This is huge, but this came with major drawbacks. 42 times higher power consumption, 42 times more physical space required, 32 times cost. This was not so efficient. So processor manufacturers have decided to create processor having multiple cores. A core is a compute unit inside the processor that can run a different program by itself. We have seen the different core on my, I've got 14 cores. Okay? And inside the cores, Intel has invented the technology hyperthreading, known as SMT by other manufacturers, which allow to switch between two functions in the same core to gain time when your processor is doing some I/O. Okay? Another point about the processor memory, quickly, this is the non-uniform memory access. Do you know what is a non-uniform memory access? You can raise the hand, just a few people, rather nobody. So it's very interesting to present it. So non-uniform memory access means that on a processor having 4 cores here, each core can be physically connected to only a part of the external memory. So it cannot access to all the memory inside the computer. Let's go back to this picture. On this picture, you see the memory sticks. And let's say this processor can access to only this memory, and this one to the two others, physically. So if this one data that is stored there, he has to ask this one to give him the data. This slows down the process. You can have a look on your computer to your NUMA affinity. So which core is connected to which memory inside the computer. So for this, I've got another computer on the internet. Okay. And I'm going to use the command NUMA ctl -hardware. This will display the NUMA affinity of my computer. So let's have a look. This says that on this computer, I've got 4 NUMA nodes, 4 CPU nodes that imply this number of cores, over CPU nodes, and over CPU nodes, so 4 groups of CPU. And the CPU node group 0 can access to the memory node 0 at a logical time of 10. This is a logical time, this is not a physical measurement. Okay, and this is the best it can do. If you want to access to the other memory node, 1, 2, 3, it costs more time, 16 here. This is still a memory, a logical time. So you can try, when you want to run a program, to say, hey, my program, I want you to run with this special memory node because I only need a few memory, 64 gigabytes, it's already good. And I want to use the physical one to which you are connected to. So you can do that with the command NUMA ctl, or I've got one somewhere. CPU node by, I say I use the CPU node 0, and the memory node 0, so with the best time of 10. And I run IPython again. Let's start. In IPython, I'm importing NumPy, and then I want to do a little computation, the sum of a random matrix. Running it, it will take 8 seconds. 8 seconds, I think. I did it a lot of time to prepare. 7.8 seconds, fine. So now I want to run the same, but let's say I haven't taken care of on which memory node I'm working, so I use the second one. I'm not physically connected to this one, so it will be slower. Let's do that. Import NumPy, run it again on the same computer. it's a bit slower. Not 1.6 times slower, but a bit slower anyway. 8.4 seconds. So you lose a little time. On very huge computation, we can slow down a lot or accelerate your computation. If some of you have used Dask, do you know Dask? We are going to speak about Dask later. If some of you have used Dask, you can run Dask workers taking care of NUMA affinity. You can have better performances. Okay, perfect. Let's go back to the slide. So we have played with the NUMA affinity, with the frequency. Let's speak about GPU quickly, and then we are going to do a bit of code. So GPU are graphical processing unit. Since the beginning of this century, GPU have included dedicated computing units for floating point operation. So they have been started to be used for data science, for doing computational tasks, and they are massively parallelized. In a GPU, you have thousands of cores compared to a few hundreds for the best processors. So GPU have a lot of cores, and they run, and so they can do a massively parallel computing task. So let's take a look to understand the differences between GPU and CPU. The best CPU and GPU we can find actually on the market. If you look at the best CPU, the best one is this one. It's an AMD EPIC. I don't say the number. And with only 200 cores. So you can run 200 tasks in parallel. It's not so bad. But if you look at the best GPU on the market actually, the best one, if you look at the number of cores, only this part, it's the NVIDIA RTX on this number, which owns 21,000 of cores. It's a lot more. It's 100 times higher than the CPU. So, wow, couldn't I just use the first 20,000 core of my last NVIDIA graphic card for computational and allocate the remaining 700, apparently, to replace the few core of my CPU, only 14 here. That way I could say goodbye to the CPU entirely, and that will save money also. Can we do that? We cannot. Do you know why we cannot? No Andres. So in a CPU, all cores are independent and can execute different programs simultaneously at a given time. So they are well fitted to run an operating system. On your operating system, you've got your web browser running, your text processors, your code editor, many different programs. On a GPU, this is the main ID. This is not strictly exact, but this is the main ID. All cores execute the same task in parallel at a given time. So GPU are well suited to do massively parallel computation. For example, on a table, you want to add +1 in all table cells. Each GPU core takes one cell and do add one inside, and they do that in parallel, 20,000 by 20,000, where your CPU can do 200 by 200 times. Okay? But you cannot manage an operating system on a GPU because all cores are doing the same thing at the same time. So GPU is fine for processing large dataset or matrix, and CPU for running an operating system. That's why GPU have not replaced the CPU. Okay, I don't reply to this question. If you have it later, I will answer with pleasure to have time to have a bit time for the examples. Okay, we have other processor. GPU are very powerful for machine learning, but they consume a lot of power. If you have a look at the best NVIDIA or this one, best AMD, it's 1,000 watts per second. It's a lot of power consumption. So in 2013, Google has estimated that to keep its growing of deep learning, it has to double its number of servers. It was unsustainable. unsustainable. So Google decided to create a new kind of processor, and this kind is named the TPU, Tensor Processing Unit. You can think about a TPU. It's the same thing than a GPU, except that you don't have the display, the video function, only the computational function specialized on matrix multiplication, tensor operation. So a TPU is like a GPU, massively parallel, but with a lower, with the lowest power consumption for high parallel task. So Google was the first one to create GPU, but now there are many manufacturers that you can find here that are producing GPU, and you can run your code on your Python code with PyTorch, for example, on any of the GPU. TPU, sorry, too many processors, kind. It's okay? So I've got a few minutes to conclude this hardware part. I'm going to try to do quick. You've got NPU, so TPU is very well for training a neural network. If you want to train a massive neural network, don't use GPU. Try to consider TPU. It may save money, save energy, and be very fast too. But if you want to just to do machine learning inference, just predict value without training, you can use the NPU. NPU is a neural processing unit specialized with very low power consumption, with matrix operation, but just for predicting values from machine learning model, not for training machine model. They are not so powerful for that. Okay? Let's finish this talk about the hardware basic and starting the parallel paradigm. When you do parallel programming, you can use different kind of programming. The actual programming we are using with Python is sequential programming. You write one function, then the others, as written here. First function, 3 seconds. Second function, 3 seconds. Last function, 3 seconds. Total, 9 seconds. Okay? You can do also asynchronous programming. Asynchronous programming in Python, or in general, in computer science, it's like hyperthreading. It's using the waiting time to do something else. Imagine that. You want to cook. You have two tasks to do, boiling potatoes and peeling carrots. Yes, you're boiling potatoes. You put the potatoes to boil, but you don't look at them all the time. You say, hey, this is boring. I'm going to switch to the other task, peeling carrots. This is asynchronous cooking. The same for asynchronous programming. So if I come back to my picture here, in asynchronous programming, on one core I run only one function at a given time, this one, 3 seconds. But when I start writing, this is an I/O. So my hard drive is working and my computer is waiting for the hard drive. I can switch to the other task. And then this one is writing at its turn. I can switch to the last one, and so on. The final on the global time is 7 seconds. So on the same core, this saves 2 seconds of computation. And finally, the best one, parallel programming, the one we are going to see right now. Okay, when you do finally parallel programming on a computer, you have two choices most of the time, multi-threading, running many functions in parallel on the same program, so this function shares the same data. And then multi-processing, running different programs, different occurrences of the same program or different programs on your computer or on many computers. If you run different programs on the same computer, on different computers, this is named distributed processing. Okay? And this is a big picture. If you want to do parallel programming, computing with Python, which library can I use? There are so many. In Python, you can do a lot of things. You can do compilation. You can compile Python code, like in C. You can do asynchronous programming, multi-threading, running function in parallel in a program. Multi-processing, running program in parallel on the same computer. On distributed programming, running program in parallel across different computers. On grid computing, this is distributed programming on different networks, like on different supercomputers. For the compilation with CPU, what do you have? That's 14 minutes, it's not so bad. NUCTA, do you know NUCTA? Someone raise their hand? Nobody? So it's a library, one people, fine. It's a that takes your Python code, convert it to C, and generate an executable that you can run. Sometimes it's faster. Python is a fork of Python that includes a just-in-time compiler, but the project is sometimes under heavy activity, sometimes very low activity, actually. Nothing happened. Hop, this is a library. You put a decorator in front of your function, and it compiles the function on the fly. This is a German function library by a German research center. It is no more maintained since 10 years, so it's an old one. But I put it here because if you want to understand how you can do Python compilation, you can have a look at the code. It is very simple, and there is no C line, only Python code. To compile Python is very surprising. PyPy, this is a fork of Python in very huge activity that's compile Python on the fly, very efficient. We are going to try it in a few seconds. Cython, I'm not going to explain all of them, but a few. This is a mix of Python and C that is converted to C, compile. Pandas on NumPy are written in Cython. Most of their code are written in Python. And when the Cython code is converted to C and compile, and then you can import it as a normal Python code, except that it's much faster. Python, another compiler. You can compile also for GPU with NUMA. We are going to try that. NUMA for CPU, GPU. Just a decorator in your front of your function, and your code is compiled on the CPU or on the GPU. It's very, very fast. JAX, it can compile on CPU, on GPU, and on TPU, especially Google TPU. CuPy. CuPy, do you know CuPy too? It's a Python library for GPU. It's a NumPy for GPU. You import CuPy as CP and use CP as NumPy. But your code is executed on the GPU. We are going to try to show that in a few moments. And you can work with Rapids AI. Rapids AI is a project on the internet. Let's have a quick look. That try to re-implement the main Python data science library for the NVIDIA GPU. So you have a Panda for GPU, this is QDIF. You have the scikit-learn for GPU, this is QML. And you have what? You have a network library like a NetworkX for GPU too. This is very fast. This is an heavy activity and very interesting. If you want to do asynchronous programming, you have a lot of libraries. The first one is async.io. I have to hurry up. Greenlight, and many others here. This library are most of the time libraries for web connection. Twisties is for web connection. FastAPI is for web server. Because asynchronous programming is about using the waiting time to do something else. So it's all about library doing connection with something else. Okay, and if you want to do the best one, distributed programming in Python, you've got many other libraries. Joblib, the one used in Celery, in scikit-learn, Celery that can run many processes on different machines, computers, Dramatic, Celery clone, MPI, this is the one used on most of all supercomputers. It can run many processes in parallel on many computers, and they can exchange data across the network very quickly. And you've got Ray for machine learning, a very good library to train your model on many computers having many graphic cards, for example. If you have a very huge model that cannot fit on only one computer, you can train it on many computers with Ray. It's very easy. This is a NumPy and Panda parallelized on one computer or many computers. We are going to try it quickly, I hope. And JAX, this is the one we have already presented quickly. That can compile Python too. And finally, for the grid computing, we have a few libraries too. Okay, these are the best I know, but there are many more. You can find many more. Sorry. At the Python wiki. So let's start with a demonstration, 9 minutes to do a bit of code. It will be short. I'm going to do my best to not bother you. Okay, let's try with PyPy, quick. So PyPy is a Python compiler. First, you install it, and you run PyPy my code, my Python script, my script.p, as you run Python your script.p. So this is a simple code, decrementing an integer and measuring the duration. I create the file, execute it with Python, near than 7 seconds, apparently. 3 seconds, sorry. 4 seconds. And I run it with PyPy. Nothing to change in the code, just PyPy my script. And attach your belt. Only 0.03 seconds. It's 100 times faster. I haven't changed anything in my code. This is very, very fast. It's worth to be there, no? So we can ask why everybody is not using PyPy. I will reply later if you ask the question. Okay, if you want to compile with something else, you said, oh, PyPy, I don't want. I prefer NUMA. So here's the typical NUMA example. I'm going to create a fractal, a Mandelbrot fractal. The Mandel function is computing the color of a pixel. And this one, with two loops nested, is calling Mandel for each pixel. So creating the function, executing the code, and measuring it. Let's run it. Beautiful picture, have a look. Perfect, and it's 3 seconds with pure Python, no compilation. No compilation. So I import NUMA. I add this only line in front of each function, the decorator NUMA.jit. And this say, compile my function the first time you execute it, then use the compiled version. And I run the same code. Attach your belt again. So I'm 10 times faster. Not so bad with 3 lines of code. But this includes the compilation time. If I execute it again, the compilation time will be removed. Let's do that on 0.05 seconds. Okay? Much faster again. There are many things to say about NUMA, but that's enough for the demonstration. Let's switch to the basic of parallel programming. I've got 6 minutes. I want to do task on that. It's very short. Let's try. So if you want to do multi-threading or multi-processing in Python, you've got native libraries, threadings, and multi-processing. Let's start with multi-threading. So I've created a function that displays 10 times the same message with a little slip. So it will be 5 seconds executing it. 1 time, 2 times, and then the main program. 15 seconds. Okay? Let's run it. This is sequential code. Then I switch back to my presentation. And let's try to explain how do you parallelize this with multi-threading. If you want to create a thread, I remember a thread is a function that is executed in parallel of the main process or the main program in your program, in your script. So I have to import the thread class that I rename task. I've said my functions, the function that I want to execute is f1 with this parameter, and I want to execute a second one with this second parameter. Then this just creates the task. This doesn't execute the task. To execute the task, I say t1.start. This starts the first function in parallel of the main program. This can be parallelized if I've got at least 2 cores on the computer. If I've got only 1 core, no parallelization is possible. Okay. Then I start the second thread here, and at this time I've got 3 tasks at the same time on the computer, so I need at least 3 cores. If I've got only 2, the last one will wait its turn. And if I want that my main program wait for the task to be completed, I can use the join operation. Let's go back to the first example. So sequentially, the code to 15 seconds. If I run it as explained with thread, it will be show your hand, 5 seconds. Okay, it should be. And we see that each function is running all together. All functions are running all together. And the messages are displayed in the same time. And the final time is 5 seconds. Fine? Welcome to the magic world of parallel programming with Python. 4 minutes. Okay. I would like to speak about concurrency. So when two functions want to update the same data, but I won't have time to explain quickly task and speak about the cache. So I'm going to jump on task. Let's have a look. So Dask is a library. Who is using Dask, actually? Can you raise a hand? OK, a bit of you. So I'm going to try to show you something nice that we have learned. And for viewers to discover a nice library. If you use NumPy and Panda have two drawbacks. They are not parallelized. So if you have 10 cores and you want to do the sum of 10 columns in a table, you do column one by one. This is not so efficient. And they all work in memory. So if they need to load all the data in memory. If you have 1 terabyte of data on only 10 gigabytes of RAM, you cannot do that with NumPy and Pandas. Dask can solve these two issues. The main idea of Dask is to cut the NumPy table in many pieces. And if you want to compute the sum of the full table, Dask will compute the sum of each pieces, then aggregate all the results to have the final sum. And this works for most mathematical functions. The minimum is the minimum of all minimum, the maximum is the maximum of all maximum, and so on. This doesn't work for the median. The median, you need to load all the data in memory, sort them to find the middle value. But for most functions, it works fine. And the main idea of Dask is I will run the computation of each block in parallel on all the core of the computer, or if I've got a cluster, on all the core of my cluster, so on many computers. This is possible across the network. So how it works? You import Dask. Yes, 2 minutes, it's just the right time. Then you do a little computation as a, how do you say, reference measurement, a normal random matrix that I compute, and I compute the mean. Running it takes 20 seconds on my computer most of the time at the highest frequencies. This is my frequency actually. 12 seconds, perfect. And now I want to do the same with Dask. So to do the same with Dask, you just import Dask array as DA and use DA as NP. So the same syntax, the same mean, just to finish, you have to say, hey, do the computation, else Dask only stores the action you have to do to process them in parallel later. So I do the computation, and I've got 14 cores. It should be 14 times faster, so 1 second. Let's do it. 1.5 seconds. That's good. I wanted it to be slower. I'm surprised. So this can be better. Can we do much more than NumPy? NumPy is working on 1 core. I'm working on 14 core. So it should be a bit lower than 1 second. Yes, we can do much more efficient. Have a look at X. X is this table. It's a table having 7 gigabytes of memory, and chunks are made of 128 megabytes. This is huge chunks. If you want to compute a chunk, it doesn't fit in my, do you remember? In my memory cache, which is only 1 megabyte. So it is too high to be stored inside this cache. So my processor doesn't work at its full speed and is doing a lot of round trip with the external memory to load all the chunks. If you take some chunks lower that can fit in the cache, we can have much better performances. It will be the final cloud, the final point. So we can do that by saying that, hey, use little lower chunks. So now my chunks are less than 1 megabyte. So they fit entirely in the cache. I run the computation again on the same matrix and attach your belt, 0.5 seconds. That's very used. This is 22 times faster than NumPy. I've got only 14 cores. How is this possible? Because of the cache. My processor can run at its maximum speed. It's okay for everybody? Perfect. I've finished. For that, if you want to run with CuPy, this is the same. Import CuPy as CP. It's run on your GPU. Let's have a look. Very fast too. On a chunk to manage here. Thank you very much.
Thank you, Gaël, for all your insights. We have before we go into coffee break, a little bit more time for some Q&As, and we have some questions. The first one, well, why is not everybody using PyPy then?
Yes, very good question, because all Python libraries are not compatible with PyPy. PyPy is compiled differently than Python, the C Python. It's a R Python motor inside, engine inside. And when you run PyPy, where is the camera for the answer? No, no camera. Okay, so I'm looking at you. When PyPy is, when you run PyPy, PyPy doesn't manage properly Python libraries that are directly calling C function, like NumPy, Pandas, Matplotlib, and so on. So each Python library using C function directly, and not only pure Python code, doesn't work properly with PyPy. That's the main reason why PyPy is not used. But since Python 3.13, there is a inline compilator, just-in-time compilator included. You have to compile Python with this online compilator, and you will get very nice performances.
Yeah, okay, thank you. And then the next question, where would you place the built-in multiprocessing library of Python inside the parallel processing landscape, and would you recommend using it?
Sorry, I'm not sure I have
Or
understood all the question. My English is not very good. So it's about all the libraries, sorry. I have a lot of things. Let's go quickly. Yes, I think you were speaking about that.
Yeah.
So, what is the question?
Multiprocessing, I think it's the typo probably. Where would you place the built-in multiprocessing library of Python inside?
Can I read the question? Sorry, I don't understand the name. Where would you place the built-in multiprocessing library? Yes, sorry. So the multiprocessing library is there, here. And if you have a look here, it should have been put, but I have not here, distributed programming. This is multiprocessing on one computer or many computers. Most of the time, many computers. But in Python, the multiprocessing library can run many programs on the same computer, but on many computers too. It can do that with managers. So it should have been put here in distributed programming.
All right. Then we have, what about polars?
What?
Next question, what about polars?
Oh, polars is one of the best Python libraries for data frame. Yes, sorry, I should have put it here. Thank you very much. So it's polar.rs. Who knows polars here? Oh, a lot of you, yes. You're clever people. So, well informed. So polars.rs is a library to do data frames like pandas. Dask can do data frame on parallelized pandas on one computer or many computers. Polars is maybe the fastest library to do data frames. The syntax is completely different from pandas. That's not so fine. If you are used to Panda, you have to learn a new syntax, and it's not so easy at the beginning. Most of the time, you don't like it. But you've got the very best performances, better than Pandas, better than Dask, and sometimes better than a GPU on a CPU. That's very surprising. Not all the time. And Polars can run on CPU, on GPU. But the only one limitation of Polars, the two limitations, the API is not the Panda API. And the second one is that you cannot parallelize Polars on multi-computers. Dask can be used on multi-computers to use all the core, all the GPU of many computers.
Thank you. We have another question that's asking, how are NPUs optimized for inference?
NPUs?
Yes.
For inference. So it's about the hardware of the NPU. Inside the NPU, you've got matrix operation, tensor operation, with a very few circuits that can do matrix multiplication and things like that on simple data. So you can do matrix product, for example, scalar product very quickly. This is hard coding in the processor. It's very fast. It consumes few energy, but it's not enough. They have not enough power to do, how do you say, machine learning training, which require much more compute capabilities. I don't know if it's enough as a reply, but you can send me an email.
So I think we have two more questions. I think we can do that and then go into coffee break.
Okay.
can you recommend resources to learn more about parallel programming in Python?
About?
Can you recommend resources to learn more about parallel programming?
Yes, yes, yes. Yes, I can do that too. My book, no, I don't have right hand book, but I will have please. Let's say there is, you know, Pack Publishing, maybe. I'm going to. So it is somewhere here. No, or let's packpub.com. So this is a book editor. I don't have any action stock in it, but there is a free learning here. And each day there is accept essential cookies only, yes, if you want. There is a free learning section. Each day you can download a free book, free. And some are on Python. And on this website you have got very nice books about parallel programming. One for GPU, Python, that I recommend. For example, GPU computing with Python, very good, or GPU computing with Python on CUDA, only for NVIDIA. This one is for both NVIDIA and AMD graphic cards. And if you want parallel programming, there are some a bit old, but they're still good anyway for the concepts. Parallel Python. Ici, Python parallel programming with Python. The two books are very nice. High performance computing with Python is nice too. They are not so young, but anyway, the library like multi-threading, multi-processing haven't changed a lot. So you will learn the basics. Fine. And you can have a look at my website. I've got tutorial about parallel programming too.
All right. Well, final question that we have here. Is it possible to process Python on quantum computers? What are benefits or downsides?
Yes, yes. Python is very good for quantum computing, like for machine learning. Python is a language for machine learning engineer. It is the same for quantum computers. There are some slide. I've got very issues with tenses when I speak too fast. So let's have a look. There is here a future section in my talk, but I was too short to show it. Let's have a look at the near future. So you can find processor having 900,000 core in the same chip. And you can use it here in Germany at the Helmut-Schmidt University in Germany. Fine. This is and you can run Python on it. And about quantum processor, the quantum processor is like a fridge. It's a bit more than a fridge. Quantum processors are using bits that are made of quantum particles. So a quantum particle can be 0, 1, or be the two at the same time, 0 and 1 at the same time. And this can change the compute algorithm to reduce some complexity, dividing, for example, an algorithm that has a complexity on n factorial to a polynomial complexity. So you can find solution where actually you cannot with traditional computers. So with Python, most of the quantum computers manufacturers are developing their libraries in Python. I think they are all in Python because Python is a language for data scientists. So it was easy to continue with Python. So you can use Python with any super quantum processors. Actually.
All right, thank you. Well, I think that's it. Now we can go into coffee break, and the next talks will start at 4:30. Yes.